Great, thanks for the introduction, Tony. Yeah, it's going to be a exciting and busy meeting today. We have 8 speakers today, so this is going to be a unique situation. I'll skip through the introduction real quickly. Most of you are familiar with IARPC, which is the Interagency Arctic Research Policy Committee. It kind of brings together an organization that brings together leaders from agencies and departments and offices across the US federal government, aim to enhance the collaboration on research in the Arctic. And the physical oceanography community of practice aims to facilitate the exchange of information, encourage new collaborations on the physical oceanography of the Arctic Ocean across agencies, and primarily through the organization of monthly webinars like this one. So the Consortium for the Advancement of Marine Arctic Science is the topic of today's webinar, CAMAS. The consortium aims to advance the understanding and model representation of key marine Arctic processes that contribute to the rapid changes in the Arctic Earth system. It is sponsored by the RGMA program element of the Department of Energy, and particularly hosted by the HILAT RASM project. And we are organizing regular workshops to enhance collaboration on marine Arctic science, international collaboration on marine Arctic science, and also by engaging the next generation of marine Arctic scientists. We had an introductory webinar back in November 2023, and since then we had 2 workshops and early career schools. And the session today aims to inform the community about the progress that has been made since. First of all, we have Jackie, who will give this overview presentation, and then we'll have about 8 speakers that talk very briefly about the projects that are leading, the collaborative projects that are leading in the context of this CAMAS organization. So without further ado, I'll hand it over to Jackie to introduce the project at large. Thank you.
Thank you so much, Wilbert. So I'm gonna share my screen here. Hopefully everyone can see that. So I'm Jackie Clement Kinney at the Naval Postgraduate School in Monterey, California. And as Wilbert said, I'll be giving you an introduction to the Consortium for the Advancement of Marine Arctic Science, or CAMAS. The organizing committee is shown here. It includes Wilbert and Milena Veneziani at Los Alamos National Lab. It includes myself and Wiesław Maslowski at Naval Postgraduate School, and then Joshua Zhang and Mike Steele at the University of Washington. And as Wilbert said, CAMAS is organized as part of the HILAT RASM project, and it's primarily sponsored by the Department of Energy's Regional and Global Model Analysis Program, RGMA. And through CAMAS, we seek to facilitate and enhance international collaboration, as Wilbert said, on Arctic marine science. And this is motivated in part and also by the demonstrated need for and the accomplishments of similar past efforts. Some of you may be familiar with AOMIP and FAMOUS. And we also want to educate and inspire a new generation of Arctic scientists by breaking down barriers for entry into the field. And as Wilbert said again, the overall aim is to advance the understanding of key marine Arctic processes that contribute to the rapid changes in the Arctic that are currently underway and that are also predicted to occur in the future. So we know that the Arctic Earth system is changing fast, and successful adaptation requires accurate predictions and projections of these changes on interannual to decadal timescales made by reliable Earth system models. And as models of the Earth system become increasingly complex, confronting them with available observations with each other in theory has proven an efficient way of increasing our understanding of key processes. And so we seek to improve the representation of these in models, which will allow us to increase our confidence in their projections. So along those lines, we have come up with 3 overarching themes for CAMAS, and these include drivers and impacts of ocean heat and freshwater transport into and out of the Arctic, ocean ice atmosphere interactions in a warming Arctic, and then biophysical impacts of marine biogeochemistry. So the activities of CAMAS, these include organizing annual workshops to bring together the community for efficient collaboration, but we really don't want CAMAS meetings to be just another meeting. Instead, the idea behind CAMAS is to provide participants with time to come up with ideas for collaborative efforts that will advance our understanding. We really hope that tangible products can be created through these meetings, and we're seeing some of that already. So, not finished here. So examples of these products and activities include collaborative working groups and publications. These could be model intercomparison studies or perhaps some model data intercomparison. We also would like to see generation of ideas for collaborative proposals, and we can envision the creation of a new data set, or participants might contribute to metrics packages that are currently being developed. And other ideas for CAMAS activities are always welcomed. So, as I mentioned, early career support is a really important part of CAMAS. And so the day before each of our main workshops, we host an early career school. And this school gives students and postdocs the opportunity to hear interesting lectures on important work from a range of perspectives and subdisciplines. We also include extra time for making connections, asking questions, and hands-on experience. We encourage early career researchers to participate in the working groups to gain experience in seeing how a scientific question can be addressed from the conception of an idea within a small group to eventually a publication. And fortunately, the Department of Energy provides financial support for many early career researchers to attend the workshop, which is a great benefit. So the first CAMAS workshop in Early Career School was held in Santa Fe, New Mexico last year in February. We had 80 participants, most of whom were in person, and this included 35 early career researchers. Participants were from the US, Canada, Europe, and Asia. And the organizing committee published an article with details on this meeting in BAMS. The citation is here. Wilbert led that effort, so you can read more about that meeting there. And workshop participants identified knowledge gaps and formed working groups around several topics. And these include Arctic Ocean mixing, freshwater distribution, Arctic cyclones, phytoplankton under sea ice, and riverine inputs and carbon dynamics. And then these working groups continued to meet online after the meeting and developed white papers outlining plans for the future. Our second workshop and Early Career School was held earlier this year, so in April in Seattle, Washington. We had 74 participants, 33 of which were identified as early career. And again, we had participation from the US, Canada, Europe, and Asia. And several of the early career researchers were really involved in the working groups that were developed, and some of the groups are being led by early career researchers with support from the organizing committee, of course. Again, the participants spent time at this meeting identifying knowledge gaps and continued working groups from the previous meeting, while at the same time, we also formed several new working groups. And these include a sea ice regime change group, another group on Arctic cyclones, and then several on Arctic Ocean processes and changes, including mixing processes, pathways of freshwater, gateway transports, water mass properties, SST regime shift. And then we also had 3 biogeochemical groups, 2 continuing from last year, phytoplankton under sea ice, and then riverine inputs and carbon dynamics, and then a new group looking at fall phytoplankton blooms. And so these are the topics that you'll hear updates on from most of the leaders of these groups coming up next. So we asked for early career researcher feedback at this meeting, and we received some feedback on things that went well and things we might want to work on. So we want to show that we are definitely taking that into account. We overwhelmingly received really positive feedback. For example, this was the most productive and exciting conference I attended. The presentations were great. The discussion time was helpful. The early career folks really enjoyed that we hosted breakfast and lunch on the meeting site, on the premises. And so a lot of connections and conversations came out of meals together during that time. And then we also left time for in-depth questions on the topics, and that was really appreciated. There's one thing we want to work on, which is the flash talks may have been a little too fast, and maybe folks are trying to cram in too much into too little time, and that might be a bit hard to absorb for early career folks. And just finally, you know, the feedback was appreciating the interactions, the interesting discussion and feedback on the early career researcher work. And so we had a lot of folks come back from the first year to the second year, and they were, you know, really invested in seeing how these projects move forward and contributing to those. So our third workshop is planned for Monterey, California, here where I am. And so we're looking at Hopkins Marine Station at Stanford University. This is a picture to entice you to come and join us. We're planning to have the meeting in April 2026. This is not set in stone, but that's the tentative plan right now. This location, as I said, this is part of Stanford University. It's next door to the Monterey Bay Aquarium. And we just hope that you would consider to join us to continue working on these collaborative projects and develop new ideas. And again, we will have early career support available. So you can encourage your students or postdocs, if you're not one, to apply for that. And some additional news for CAMAS is that we have created a special collection with the American Geophysical Union. And so this is a CAMAS special collection. You can submit to 5 journals, including JGR Oceans, GRL, James, Biogeosciences, and then JGR Atmospheres as well. So this special collection is open now, and it will be through May 2027. It's really simple to, you know, submit your manuscript. You just go through the regular submission process, and then you select the CAMAS special collection as a drop-down option as you're submitting your manuscript. So we encourage people to consider that. It doesn't have to be just a project that was only done at CAMAS. It can be related to all the different themes I've mentioned. And so just finally, if you have questions or ideas, we'd love it if you email us. This is a link for the organizing committee. Here we are at our meeting in Seattle at the end of it. And just finally, if you're not already signed up for the mailing list, please consider doing that. The QR code on the left will take you right to the sign up. It's very simple. We will not spam you. We'll just provide you good information. And then the website is on the right-hand side. So that's basically it for me. Thank you so much.
Great, thank you. Thanks so much, Jackie, for this overview. Yeah, just as a quick follow-up on the meeting, the next CAMAS workshop in Monterey, we're still talking with US Cliver. They're planning on organizing a workshop on Arctic Ocean climatologies, and we're trying to kind of co-locate that with our CAMAS workshop, both in space and in time, to reduce the number of travel that is required. But I'm pretty sure that each of these workshops would be relevant to a large subset of potential participants. So keep an eye out for that. We're finalizing that right now. So great. Yeah, so as Jackie said, we have several ongoing projects, about 10. 8 of those projects are being represented here today, and it will give a brief overview in the next half hour of what their plans are. And it's not just to give you an idea of what CAMAS is working on, but also to gain potential additional interest from modeling groups and observational groups to participate. So we'll start with a presentation by Claire Gaffey. She is currently on the Healy, so she's not able to join in person, but she gave us, she pre-prepared the presentation that I'm going to try to share right now. So that is going to be our first. Then it's going to be followed by Colin Schmidtgall, Kylie Liu, Rujan Gu, which is also a pre-recorded presentation. Then Harry's going to talk, and Sawyer, Georgina, and finally, Jackie is going to give an overview of her project on under-ice phytoplankton. All right, so I'll hand it over to Claire. Let's see, we did try this. We really did. Application windows. Oh yeah, I never know which one to get. Sorry about that. This one. That's it. All right, I think we're good. Stuff from here.
Hi, hello from the Healy. My name is Claire Gaff. So typically in the fall season, you are deplete of nutrients in the upper water column, with the nutrient concentrations mostly being held coming through that are powerful enough to mix down into the nutrient, then you can have more of those nutrients available in the upper ocean and make those.
Wilbert, I can't see anything. Oh, there we go. Just
Yeah.
appeared. It just
Yeah,
Emphasize this link between
Can you hear it?
storms.
yeah.
Can you start over, Wilbert? Uh-oh.
Wind speed and high wind events, maximum wind speed, all of which really didn't have much of an impact when compared with other variables as well.
Yeah, we
so
can still hear it, but we don't see anything anymore.
Let's break down what are the real physics.
Okay. Not sure why not.
Yeah, and we can always come back to that one if you'd like, if we want to keep us moving. Maybe Carlin can go.
See my screen or not?
No,
Not
anymore.
yet.
Jump in.
Sorry. You cannot see my screen anymore?
Not anymore.
Okay. Well, let's hand it over to Carlin then.
All right, sounds good. Thanks. All right, I'll share my screen. View slideshow. All right, is that coming through for everyone?
Yes.
Yes.
Awesome. All right, well, nice to meet those of you I haven't met before. My name is Carlin. I'm a grad student at the University of Washington, and I also do work at Los Alamos National Lab. And I'll be talking about a project I am co-leading along with my advisor, Wilbert, and graduate student Teowie Skibbins, who's at the University of Alberta. And this is a project looking at freshwater pathways across the Arctic Ocean. And so the overarching goal of this project is to connect the pathways of freshwater sources, in particular, ocean inflow and rivers, to changes in freshwater content and stratification within the Arctic Ocean. And in particular, we want to explore the interannual variability of these processes and how they depend upon atmospheric forcing conditions, such as the Arctic Oscillation or the Beaufort High. And so this is a model intercomparison project where we are carrying out a series of coordinated Eulerian dye tracer experiments in ocean general circulation models, where we're tagging various inflows into the Arctic Ocean. And so to look at the impacts of different freshwater sources, we've kind of split into two sub-experiments. We have an experiment that's looking at oceanic contributions to freshwater sources. So this is led by myself and Wilbert, and then an experiment looking at how rivers are impacting the freshwater balance in the Arctic Ocean. And this is led by Taya. And so I mentioned that we're interested in looking at the interannual variability of kind of the freshwater pathways. And so one of the unique things that we're doing in this experiment is, rather than doing a sustained release of tracers, we're going to be releasing tracers in kind of a series of pulses so that we can compare the pathways that water masses take across the Arctic Ocean and how this varies from year to year. And we're planning on targeting a period in the Arctic Ocean from 1992 through 2001, where the Arctic Ocean was releasing fresh water for the first part of that time period, and then accumulating fresh water for the second part of this time period. And prior research has connected this to influence from atmospheric parameters such as the Arctic Oscillation. So we'll be focusing on this time period for our model runs. Briefly looking at some of the kind of first output of the simulations we're already carrying out at Los Alamos National Laboratory in E3SM. So this animation here is showing one example of one of these simulations where we are tagging all of the oceanic inflows into the Arctic Ocean. You can see Pacific origin water tagged in kind of blue-purple coming in through the Bering Strait, and then Atlantic origin water tagged with kind of shades of blues and greens. So we're releasing these tracers for 1 year. We turn off the source, and then we follow these water masses as they advect through the domain and kind of follow different pathways. And the goal is to compare how this changes from year to year. A little bit of a first look at what some of this analysis might look like. So I'm showing here our 4 time series of integrated tracer volumes computed across different regions of the Arctic Ocean. And calculated for different like tracer release years, 1990, 1992, and 1993. The upper panel shows total tracer volume for the entire Arctic Ocean. So you can see this gives us a sense of the residence time of Pacific origin water in the Arctic. And then those lower 3 panels have broken this down into different sub-regions of the Arctic Ocean so that we can trace these pathways. This analysis is just looking at volume tracers, but we'll also be doing an analysis looking at how this is impacting the freshwater content in these different regions of the Arctic Ocean. And so I mentioned we're also looking at the influence of rivers on the freshwater balance. And so this is something that is being kind of spearheaded by Thea at the University of Alberta. Here's an example of some output in E3SM showing 1 year of tracer release for kind of the 4 major Arctic rivers that we've identified. And forthcoming experiments are also going to include the Yukon River as well. And so overall, this project is aimed towards deepening our understanding of how freshwater moves through the Arctic Ocean and how this varies year to year with different atmospheric conditions. We're currently carrying out experiments in E3SM Arctic at Los Alamos National Laboratory, and we've identified several modeling teams that are interested in collaborating with us and also contributing model experiments towards this project, which we're really excited about. And with that, I thank you for listening. Please reach out to me, Wilbert, or Thea if you have any questions or comments. Thanks.
Great. Thank you, Carlin. Kylie, do you want to share?
Sure, I would like to share. And could you see my screen right now? Okay.
Still working on it on my end. Yes, this looks good. Thank you.
Yeah. Okay, hello everyone. I'm Kerry, and now I'm a postdoc in the First Institute of Oceanography in China. So I don't prepare some slides, but I prepare for a document. This is our research design about the Arctic cyclones. You know, this topic is built on the extension of CAMAS 1, and we discussed this topic about storm Mabok, which is a extra typhoon travels from the tropical Pacific and move to the Arctic regions in 1 week, and it caused very huge disasters around Bering Sea and Alaska. You know, so I think based on the first CAMAS 2 discussion in May, so we decided to have a detailed look about these Arctic cyclones, these tropical cyclones, you know, move forward. And about the introduction, the Arctic storms is important too. Has great importance. Has great role in playing the to impact the Arctic environment. So we do some literature reviews and to initiate our topic. Yeah, and the second point is that beyond the regional impact. the tropic Arctic connectivity has emerged as a critical component of the Earth's climate systems, and so the tropical cyclones can move from the tropical regions to the Arctic regions. And so this one of our motivations. So this is introduction of the MABOC, and it starts from about 911 in 2022, and it moved northward Pacific to the Bering Sea in about on about September 16. So in 1 week, it has a first checks, and you can lead to great oceanic changes such as the sea surface temperatures anomaly along its stone shakes. So I think firstly we may have a look at the surface changes led by the MABOC, and our research goals has 2 points. The first one is to investigate the oceanic responses during the MABOC in September the 14th to the 21 in 1 week. And firstly, we will collect some observational data to review the surface changes, and then we will combine some model simulations from NEMO output, and to have a look at the oceanic changes in mixed layer depths and the ocean interiors. So the second point is to identify the physical drivers to explain why the ocean has these changes, especially for the heat flux aspects. And so the current advances for this research is that we prepare for some data, especially for the observations from Sassy and near the Berlin and Beaufort coast, and some mooring data in Chukchi Sea. So our research area is on the Berlin, Beaufort, and Chukchi regions. And we will also combine with the NEMO simulations. Fortunately, we have the power from the University of Alberta to join us, and he will offer us some NEMO simulations in a quarter resolution, and even 10 one divided 10, 0.1 degree resolution. So we will combine the observations in the 2 resolution model output to investigate the oceanic changes during the MABOC. And we have some preliminary results. Firstly, we want to show the MABOC case, in the 5.1. So we will to plot the MABOC checks and to show the sea surface temperature changes. And this figure shows that the left is the September mean. Is the day on September 18, and relative to the September mean temperature anomalies, and we can find that the MABOC it actually leads the cooling in the North Pacific, but inverse, the Bering Strait seems like it is a warm anomaly. So I think this is an interesting phenomenon, but we have to combine the model output to have some comparisons and to offer some insights. And so in Figure 2, in our research design, we will adopt the NEMO in multiple resolutions, and to compare with the observational sea surface temperature changes, and then to have a further investigation of the mixed layer depth changes.
Would you mind
Yeah.
wrapping up?
So what?
Would you mind wrapping up?
Would you mind? You mean, sorry.
Yeah, so you're at your time. So
Okay, sorry. Okay.
that's right.
Yeah,
So-
yeah.
So final words.
So in our plan, we have to evaluate, least storms, impacting the Arctic environment, and compare the observations in the two different resolution data sets, and to offer some evaluation and explanations. Yeah, this is
Great, thank you very much.
okay.
All
I
right.
will stop the screen. Yeah.
The next up is Rajan Gu, and that's a pre-recorded presentation that Tony will share.
Hi everyone, I'm Rijian. I'm a postdoc at Laoshan National Laboratory. Today it's my pleasure to introduce our CAMAS project. The 2007 marked extreme sea ice loss, and we find in that year sea ice become fragmented, especially in the marginalized zone. And we find there is a sudden surge by 0.8 degree and a double variability at the ocean surface within the marginalized zone. So this is the summer SST anomaly. The increased variance marks the noise-induced transition, and the noise refers to short-term external perturbations. This noise can shift the mean state to another state. The noise in this context is the short-term extreme heating events, namely the RT marine heat waves, and we find they became much stronger after 2007, following the more fragmented sea ice. On the right-hand side, you can see two typical marine heat wave events, and you can see much stronger after 2007. And the noise has an impact on the mean state. Here is the idea. So during marine heat waves, stronger sea ice melt, that would cause more occurrences of open water and absorption of solar radiation, amplifying the Arctic Ocean warming. We quantify the causality on the right-hand side. So between marine heat wave and SST, and we find that causality became stronger after 2007 as well. And we use composite analysis, and we find the impacts on sea ice melting and solar heat input from marine waves has increased after 2007. So here is a summary. So there is an abrupt shift in Arctic Ocean warming due to increased extremes. And this shift occurs when sea ice becomes thin and fragile, meaning more open water in the marginalized zone, and it is triggered by the marine heat waves. After this point, the Arctic Ocean enters a new state with more sea ice melting and solar heat absorption. And the analysis is based on observational data sets. And the motivation of our CAMAS project is to evaluate model scales. At this stage, we are looking into the model scales in climate models. We find the CMIP6 models generally project delayed timing of the abrupt shift, and the only model, the ECRC3 model, that can generate the shift in the historical period, has a stronger causal relation among marine heat wave sea ice and SST compared to the other CMIP6 models. Here is a plan for the CAMAS project. We want to examine this 2007 shift and the related mechanism in HINCAS models. The advantage of HINCAS model is that we can specifically look at 2007 to see if there is a shift and what the mechanism would look like. One thing that I'm wondering is the resolution effect, because high-resolution models generally simulate stronger and more realistic marine heat wave intensity. At the end, I want to advertise the research issues group that I'm leading. So this is meant for a collaboration platform, and we have a college work group and a machine learning work group, respectively, for interdisciplinary research and model development. This physics work group recently focuses on the following physical questions. I welcome collaborations. Thank you.
Great, thank you. And next up is Harry.
Okay, hello, can you hear me?
Yes, we can.
Okay, I'm not going to share a screen. I don't have any slides. I'll just, so I'm working with the sea ice regime shift, and we are focusing on sea ice extent and sea ice thickness, just those two variables, and the shift that sea ice extent and sea ice thickness underwent in the year 2007, in the summertime of 2007. And so we have a draft paper. I mean, it's really just an outline. It's got an introduction and it's got sections on the kind of model output that we would like to see in order to compare with observations. And in the chat, I posted a link to a Google Drive folder that has a copy that has a Word doc that's kind of an outline of what we want to do. So modelers who are into sea ice, have a look at that and see if you would like to contribute to that. And that's about all I have to say, unless Mike Steele wants to add anything to that.
Nope.
Okay.
Great, thank you. And just as a reminder, Harry gave a presentation maybe a month ago
Yes.
about this topic, and maybe I can dig up the link to that presentation to share. Okay, we'll hand it over to Sawyer.
Thank you. Let me know if you can see my slides. Are they sharing appropriately?
Yes, looks great.
Okay, great. Hello, everyone. My name is Sawyer Brand. I'm a postmaster student at Los Alamos National Lab as part of the HiLab RASM project. And I will be talking about a CAMAS project that we just started, myself and my co-lead, Joshua Zhang. And what we would like to do is to take a look at Arctic Ocean stratification. Let's see, okay. As we all know, the Arctic has a really harsh climate that leads to spatiotemporal coverage issues within observational data. And so the purpose of our project is to use a self-organizing map, or SOM, which is a machine learning technique, to compensate for holes in the data in the coverage that we have in observations. So we will be using a multivariate SOM on CTD and nutrient data in the Chukchi and Bering Seas to try to link to classify stratification patterns and then try to link them to nutrient distribution in the local region. So this is inspired by a paper by Erin Thomas and her co-author in 2022, where they used a SOM on profile data within a model, if I remember correctly. And so you can see the SOM output that they get. It's a range of profiles, characterizes possible stratification patterns in the region. And so we will be mimicking this, but using a multivariate SOM that links these profiles, like the ones you see on the screen now, to the associated nutrient profiles in the region. Our major goals for this project are to perform that analysis, classifying stratification patterns and maybe doing some water mass analysis, link it to impacts on local nutrients, and then move into a model ensemble and using the same SOM that was created with the observational data. The observations we're using are ACOD, the Alaskan Compendium of Ocean Profile Data, which is either already public or will be very soon. It's CTD data as well as nutrient data, and you can see the location of these data on the screen right now. We've started this project, an initial SOM has been done, but SOMs take a lot of tweaking, so the initial SOM is essentially useless. And then we'll be moving into temperature, salinity, et cetera, and trying to link the physical to the biogeochemical. So again, this project is only just starting, but we're attempting to bring together early career and later career scientists from a variety of institutions within this project, and maybe have a couple of kind of shoot off papers on similar topics as well. So that's my email in case anyone is interested. Thank you.
Excellent, thank you, Sawyer. Much appreciated. Georgina?
You hear me now?
Yes, ma'am.
Okay, perfect. Sorry about that. Great. So we, and when I say we, we've been quite a large group. We've had some great engagement in this project through CAMAS. In the first year, I think we had about 14 participants. And then we met earlier this year, and we had about 14 again. with at least 7 of those being repeat participants. So we've had nice continuity in this project. And our focus is the impact of riverine inputs into carbon dynamics in the Pacific Arctic. The motivation for this is over the last decade or so, there's been quite a bit of improvement in the treatment of rivers in Earth system models in particular, which are a little bit behind regional models. But overall, we've seen vast improvements in many of the models that simulate the Arctic. And the importance of riverine drivers in the Arctic Ocean is not well defined. And as we all know, might well be changing because of climate change, impacts to permafrost, impacts to the river nutrient and carbon loading. So our goal then is essentially a river MIP, a multiple model into comparison. So we're going to compare the results of multiple regional and Earth system models to determine the relative importance of river inputs to the Arctic Ocean ecosystem dynamics, particularly focusing on carbon production of carbon flux, DOC, for example. This is a pretty big question, and there's a lot of rivers in the Arctic. We have decided for this sort of first go round, we're going to focus on the Mackenzie River as a case study. So all models capture the Mackenzie River at least at a resolution of about 10 kilometers. So we're comparing our models in terms of how they treat the river inflow, how it's added to the ocean, sort of the logistics of that in terms of how it's spread, the depth, for example. And then the representation of each of the river drivers in the model, and then the resultant impact that we see within the ocean model itself. So that's a brief overview. It's not moving. Let me get, there we go. Okay, so our approach to this. Riverine behavior is very seasonal. So we really want to focus on the model's ability to capture this seasonal behavior. And because we're doing that, we want to have a much higher resolution output than our models traditionally provide, which is usually monthly averages. So for the years we are interested in, we're going to rerun these years to get a much higher resolution output. So for now, we're going to start with 3 high resolution simulations. So we're going to do 2009, which we've identified as a year that has a lot of good observations around the Mackenzie River outflow. We've examined Mackenzie River outflow data in the ArcticGRO database. And 2019 is a particularly high flow year, followed by 2020, which is a low flow year. So we're going to run those 2 years consecutively. So our metrics that we're going to look at within each model, we're going to identify the bounds in the Mackenzie River plume, which we're saying is anything less than 27 PSU. Once we've identified that spatial area, we're going to compute the variables we're interested in over that area down to 40 meters. And then we're also going to compare transects from the river mouth to the edge of the plume. So the table on the bottom left is the models that are currently have been identified as definitely participating in our project. So we have 6 different models. They're all representing the river to some degree at the moment. And over on the right, we have point person for those. Over the table on the right is the variables that we're comparing. So we're comparing various physical, chemical, and biological variables with the hope that we'll be able to see one. So our main goal isn't to say this model is doing this better. Our goal is to understand what is important in terms of capturing the dynamics that we observe. And then I just have one more slide. So our timeline, because we're hoping that many of you might want to get involved. So this is what we're hoping for. We're hoping to get any outputs that want to be included in our comparison by the end of the year. We'll have our preliminary comparisons by spring 2026, which hopefully right before the next CAMAS meeting that you heard about. And then a draft manuscript sometime in the summer. So that's what we're shooting for. So how to get involved. So we're currently meeting bi-monthly. And our next meeting will be September 25th at 5 p.m. Mountain Time. And so we'd be interested in anyone that has observations, either in the river or within the Mackenzie River plume. And not just the years that I mentioned, would be interested in other years also. Or if you are involved in another model that you think might have relevant output. So we'd love to hear from you. And there's still time at this point to be involved in our work. So just shoot me an email if you want any additional details. And yeah, thanks.
Great. Thanks, Georgina. And again, over to Jackie, and then we'll try one more time Claire's presentation.
Okay, so my group is working on a model intercomparison study looking at under ice phytoplankton growth. So we're talking about pelagic phytoplankton found under ice. This is a list of all the people who've been involved so far. We wrote a white paper last year, and now we have 7 modeling groups interested. We're welcoming new groups. We have a target journal of JGR Oceans, part of the CAMAS Special Collection, which we're hoping to submit to next year. So under ice blooms, they were previously believed to be negligible until maybe the last 15 years or so. They're very hard to observe, as you can imagine, and so we have limited observations of these. And so, you know, that makes it difficult to understand how important are they to the entire carbon cycle of the Arctic. We think they're probably really important, but we want to bring all of these modeling groups together to see how they're representing this process and get some intercomparison on this topic. So basically, under ice blooms, they develop in the late spring and the early summer when the water column begins to receive more light and then also becomes more stratified. And so, yes, how do models represent under ice blooms? Are there spatial and temporal trends? These are all things that we're hoping to do with this modeling group, which also has observational people as well. So if you're an observational person, we welcome you as well. So the results that we want to compare, so model output anytime starting in 1958 to the present. Runs do not have to cover that entire time, but we're looking at nitrate and silicate in particular. Then we're looking at chlorophyll A and primary production, both in open water and under ice. And then we have some thresholds for ice concentration. So with ice concentration being, you know, less than 15%, we're considering that open water, 15% to 50%, you know, and then these different bins so that we can find out, you know, how important are these blooms, because, you know, satellites can't see this and very few observations. So that's the overall goal. We also want to look at ice-associated primary production as well, so a separate thing. And then the photosynthetically available radiation, sea ice area, the total for the Arctic and interior seas. We will compare with observations as available. And then we may, if feasible, look at phytoplankton functional groups and changes over time. That might be a follow-on topic, though. That might be more than we can take on. So we had an initial data call from our modeling centers that was due in July. Some people had runs available, some people did not. Some people are still working on simulations, and that is fine. So we're hoping to have all of the model results by the end of the year. And then my perhaps overambitious goal is to have a submission of the manuscript early next year. And that is probably not going to happen in that time frame, but, you know, we're trying. We meet in the same sort of time scale as Georgina's group on the riverine. So we meet on the even months at the same time. If you're interested, please get in touch. It's easy to find me. And we'd love to include you in this topic. So thank you.
Thanks, Jackie. All right, let's try Claire's presentation one more time.
Hi, hello from the Healy. My name is Claire Gaffey. I am a postdoc at Oregon State University, and I am introducing our CAMAS group, Fall Blooms, which is in parentheses here because that's our short name, but we are interested in looking at the connections between fall storms and fall phytoplankton blooms. So in recent decades, there has been overall increases in primary productivity in fall months. So you can see a few snapshots in August and September here, with a lot of green in the Bering and Chukchi Seas. So we're looking at the connection between storms, including Typhoon Merbok pictured here as well, and their influence on these fall blooms. So typically in the fall season, you are deplete of nutrients in the upper water column, with the nutrient concentrations mostly being held in deeper water. So if you have storms coming through that are powerful enough to mix down into the nutricline, then you can have more of those nutrients available in the upper ocean and make those available for fall phytoplankton blooms. So this makes a lot of sense, and there's papers that do emphasize this link between fall storms leading to fall blooms, but it's not completely straightforward. For example, I included this figure from a paper that is about to be in press. I just submitted it with minor revisions last night. Very exciting, but in this we actually looked at the dependence of fall blooms on wind speed and high wind events, maximum wind speed, all of which really didn't have much of an impact when compared with other variables as well. So we are hoping to actually use modeling to help us break down what are the real physics of how influential fall storms are for creating fall blooms in the Bering and Chukchi Seas. So to get at this question, we're looking at a suite of observations using satellite, chlorophyll, mooring chlorophyll and oxygen, as well as underway observations from ships. So this is an example of what that data looks like that can give us an idea of productivity throughout its course. And we're looking at years with high cyclone activity and low cyclone activity. We have a suite of models as well to help us get at that question. One thing that I did include here is that we are also interested in looking at one-dimensional model runs that could be useful for separating out compounding factors. So we're looking at what are the boundary conditions for wind mixing that would spark a bloom versus actually pull phytoplankton out of the mixing layer, as has been observed in the Antarctic as well. So my email is down there. Please feel free to reach out if you're interested in our project. I'd be happy to hear from you. Thanks again.
All right, perfect. Well, thank you all very much for giving an overview of the work that you're doing. I think it was very useful. And if anybody has any interest in participating in any of these activities, then please reach out to the project leads. We are getting close to the top of the hour, and I know that Tony still has some announcement that she want to make. So again, thank you all for your presentations, and then we'll hand it back over to Tony.
Yeah, thank you, Wilbert. Thank you to all of our speakers, and thank you to everyone for being here today. I'm sorry for stealing our last couple of minutes, but I just wanted to share an announcement. I'll pop a couple links in the chat and then speak to them. But the public input period to inform the 2027 to 2031 Arctic Research Plan is now open. For anyone who's not familiar, this plan helps coordinate our overall federal effort in Arctic research. And while this is a federal plan, IARPC is seeking input from everybody with research interest needs in the Arctic. So very important that we've got fed and non-fed input alike on this plan. So I put the link in the chat to the Federal Register notice where you can submit comments. Those can also be submitted via email to that IARPC plan@nsf.gov email that's in the chat. But I know this was not a very super deep dive on what an update is, what the timeline looks like, anything like that. So IARPC, along with Navigating the New Arctic Community Office and ARCIS, are going to be hosting an information session on September 18th. So I've also put the link to register for that information session in the chat, where we'll be able to dive a little bit deeper into the process, kind of like what is the plan, how is it going to get updated, and then how is that plan used. We'll also be following that up with some information sessions with some of our IARPC collaboration teams to get a little bit deeper into the content of what each team works on and maybe what we would want them to be working on under the next plan. We'll also cover those at this information session, but this will be kind of our kickoff to all of that. So love to see you all there. Again, registration links in the chat. It's also on our IARPIT collaborations website for folks who are members. And thank you again for everyone for being here.
All right, anybody has any final thoughts before we close? Well, if not, thanks everybody, and hope you have a good rest of the week and a good weekend and all. So thank you for attending and for presenting. Take care. Bye-bye.
Thanks all.
Thank you, everyone.